Hello everyone and welcome to another Nordic Tech webinar. This webinar, Developing Low-Power Wi-Fi 6 Products, is a crash course to quickly get you up and running with a Wi-Fi 6 prototype using Nordic's hardware and SDK. You're going to learn how to connect to Wi-Fi, securely connect to an MQTT broker, and use available power saving modes to optimize for low power. So let's get started. My name is Heidi Soli, and I'm going to be your host and speaker for this session. I'm a senior product marketing engineer at Nordic Semiconductor, and I work on the Nordic Developer Academy team, creating courses there. Some practicalities before we get started. This session is going to be an hour long, 45 minutes for the presentation, and then 15 minutes for Q&A at the end. Please ask questions during the presentation. You can use the questions sidebar on the top of the right to ask questions. All questions are anonymous. Try to keep them relevant to the topic, of course, and then we're going to answer them in the session at the end. The chat on the bottom of the right sidebar is not anonymous, so don't use that for questions. And if your question is not answered at the end, or you suddenly have more questions, you can go to DevZone, make a ticket there, and you will be assigned one of our very qualified technical support engineers and get your question answered. This session is recorded, and a recording of the webinar will be available together with the presentation at the URL at the bottom. So now that that's out of the way, let's get into our agenda. First, we're going to go over some theory, a quick introduction to Wi-Fi 6, and go over the NRF70 series, which is Nordic's Wi-Fi 6 offering. And then the hands-on is going to be the largest portion of the session, where I'm going to show you how you can develop applications for our hardware that do the following things. First, I'm going to be connecting to Wi-Fi and securely storing the Wi-Fi credentials. That's part one. And then in part two, I'm going to connect to an MQTT broker using an MQTT API available in our SDK, and then add TLS on top to secure that connection. And lastly, we're going to use the Power Profiler kit to measure the power consumption on the device and compare different power saving modes, including target wake time, which is the new power saving mode introduced in Wi-Fi 6, and try to optimize for low power. And at the end, we're going to have a Q&A session, as I said. A quick introduction to Wi-Fi 6, which is the latest adopted standard from the Wi-Fi Alliance and is also the standard supported by our hardware. What is Wi-Fi? I'm sure everybody listening knows Wi-Fi, but let's get some of the terminology clear. That's going to come up again and again in this session and in the course as well. So Wi-Fi is a family of wireless network protocols. It is based on the IEEE 802.11 family of standards, which defines the physical layer and the medium access control layer of the network stack. So the two bottom layers of the stack. And Wi-Fi is the kind of marketing name for this family of standards promoted by the Wi-Fi Alliance. The latest addition to this family of standards, called 802.11ax, but more commonly known as Wi-Fi 6, came out in 2021 and had a lot of enhancements for low power and Internet of Things applications. So it's the one that Nordic kind of introduced our Wi-Fi offering with. So Wi-Fi itself is built on two main device categories. You have access points and you have stations or clients. The access point is the main central node in the Wi-Fi network. It broadcasts a wireless signal. To allow other devices to connect to the network. And then the stations or clients then connect to the access point. The stations and clients are usually mobile phones or tablets or laptops. Some literature defines stations as any device that has the capability to use the Wi-Fi protocol, meaning access points are technically classified as stations, but in the session and in the course as well, these terms are mutually exclusive to make it easier to understand. So when one or more station connects to an access point, they form a wireless local area network, which is referred to as an infrastructure basic service set, a BSS. And a BSS is the most common scenario when discussing Wi-Fi networks. And these networks have a name that are used by the clients during the connection process. This name is called the Service Set Identifier, the SSID. And this SSID is user-defined, as I'm sure anybody moving into a new house and setting up your Wi-Fi network, trying to come up with a clever Wi-Fi name knows. SSIDs are set by the user and they can be altered. So for an extra layer of security, we also have using the MAC address of the access point as another identifier, which is known as the Basic Service Set Identifier, the BSSID. When it comes to frequency bands, the standard itself specifies many frequency bands for Wi-Fi radios, but the two most common ones and the ones that are supported in Nordic Wi-Fi radios are the 2.4 gigahertz band and the 5 gigahertz band. So when making a Wi-Fi application, the choice of the band is going to be dependent on the application's specific needs and the environment it's going to run in. But a general rule of thumb is if you want long range and good obstacle penetration, go for 2.4 gigahertz. But if the application needs high speeds or a lot of devices connected at the same time, 5 gigahertz band is the way to go. Then let's take a closer look at the enhancements that were introduced with Wi-Fi 6. However, there's only a subset of these that are relevant for low power connectivity and for the Internet of Things, and that are supported in Nordic hardware. So we are going to be focusing on these 5. I'm going to explain OFDMA and target wake time in the following slides, but for the other 3, beamforming is a signal processing technique where the transmitter's antennas focuses the radiated signal towards a specific receiving device, which is different from the conventional omnidirectional radiation pattern. Longer symbol duration means the Wi-Fi 6 introduction increased the number of subcarriers that are in the frequency spectrum, which means each subcarrier is now narrower, which in turn gives longer symbol duration. And BSS coloring is a technique where, remember, BSS was the individual Wi-Fi networks. So BSS coloring adds a different color to each individual BSS. By color, it's a 6-bit field added to the PHY header of the Wi-Fi frames. So when a device is going to transmit, it can sense that channel first, and then if there are any packets there from a different color, so a different external network, it can treat them as noise and transmit over them. So OFDMA. First, OFDM, orthogonal frequency division multiplexing, is the modulation technique used in the Wi-Fi technology. And this divides the frequency spectrum into available subcarriers. And Wi-Fi 6 actually increases the amount of subcarriers by 4 times. And then Wi-Fi 6 adds orthogonal frequency division multiple access on top of that. This gives a frequency multiplexing ability, which means multiple users or multiple clients can access the same time segment at the same time. So if you see the image at the bottom here, a lot of clients are accessing this, or kind of sending or receiving at the same time by accessing this different parts of this time slice. Here's another image showing the utilization of the available frequency spectrum, first for OFDM to the left here in Wi-Fi 2 to 5, and then how it's different in Wi-Fi 6 with OFDMA. So as you can see, OFDMA allows multiple users to use the same time segment, which utilizes much more of the spectrum. And then lastly, we have target wake time, which is a new power-saving mode that allows devices to sleep for longer. So in legacy power-saving mode, how it works is that the Wi-Fi clients or the stations that are connected to the access point, they have to wake up for a beacon that's sent out by the access point at regular intervals called the beacon interval. They wake up to listen for the beacon, and then they check if there's any buffered data for them to receive. And the longer the beacon interval, the longer they can sleep. But this interval is determined by the access point, which means all the devices that are connected to that access point have to wake up at the same time, even if they have different power needs or something like that. And since the access point is only able to send or communicate with one of the devices at a time, if there are more than one devices that want to receive data packets, they have to stay idle, waiting for the access point to be ready with the previous client before they can receive their buffer data, which also drains battery. So target wake time is a new power saving scheme in Wi-Fi 6 where the stations can negotiate the wake up schedules individually with the access point, and they're not bound to this beaconing period. So stations can wake up at the negotiated times to send and receive traffic. And this is much more flexible, first because clients can actively participate in the negotiation of the scheduling with the access point, and they don't have to have the same schedule as all the other clients connected to that BSS. These schedules can also be dynamically renegotiated without needing to drop the target wake time session and renegotiate from the beginning, saving a lot of power. And it's also much more long term. So devices can sleep for longer intervals, hours, days, even weeks, which means it's a very good power saving scheme for IoT devices that sometimes, say, a sensor that only has to wake up every day or every week to send some data. So this is a very important feature that makes Wi-Fi 6 very good for these applications that wasn't available before. Now I'm going to walk you through the NRF70 series of Wi-Fi 6 companion ICs. So this is the executive summary of the NRF70 series. First, let me explain what I mean by the Wi-Fi companion IC device. So this means that the NRF70 series can be used to add Wi-Fi capabilities to another microcontroller. So you need a microcontroller as a host to run the NRF70 series device. In our development hardware, we use the NR5340 SoC, but you can use any of our chips, or you can also use an external host MCU. So as I said, the NRF70 series is dual band capable. It has support for 2.4 gigahertz and 5 gigahertz. It has a Wi-Fi radio with low power capabilities, not just because of the power saving mode available in Wi-Fi 6, but the sleep current in the device itself is relatively low. And we also support advanced Wi-Fi security features, and there is support for ideal coexistence with Bluetooth LE and other 2.4 gigahertz radios. And the device is supported in our NRF Connect SDK, as we're going to see in the hands-on session, and it comes with a Wi-Fi 6 certifiable stack, which means you can make end products that will be Wi-Fi 6 certified. The NRF70 series contains 3 different products that are listed here, from most expensive to the left to cheapest to the right. The NRF7002 is the one with the full feature set, and that's the one we're going to be using today. And then you have the NRF7001, which only has support for 2.4 gigahertz, so the 5 gigahertz band is not supported in that variant. And then lastly, we have the NRF7000, which does not have support for SDA mode or station mode, meaning that it doesn't have the ability to connect to an access point and act as a station. It can only scan for nearby Wi-Fi access points, and then it uses that information in a lookup table to assess or to figure out its location. So the NRF7000 is intended for SSID-based locationing. So let's take a look at the communication stack. This is a simplified version of the network stack that is taken from the Wi-Fi course. And as you can see here, most of the stack is located in the host MCU. So the NRF70 series itself just runs the Wi-Fi physical layer and the MAC layer, and then it communicates with the host MCU through SPI or Quad SPI. And then the host MCU is running a Wi-Fi host stack, which has the Wi-Fi driver, and then it also has a WPA supplicant, which implements the Wi-Fi security protocols. And then on top of that, you have the NRF Connect SDK based on Zephyr RTOS that offers a rich set of tools and libraries for developing Wi-Fi applications. You can see here we have TCP or UDP sockets, TLS, CTLS for security, and then we have some application protocols like CoAP, LWM2M, MQTT, HTTP. So these are all driver APIs that are available in the SDK and that are supported on the device. As for development hardware, we have many variants. They're all based on the NRF 7002, which is the device with the full feature set. So we have a development kit. That's the one I'm going to be using today. This has the NRF 5340 as the host MCU, and the DK also has LEDs and buttons. It has antennas both for 2.4 gigahertz and 5 gigahertz, and pins for measuring power consumption, and it has much more. The evaluation kit is a shield with Arduino form factor, and it fits on top of our existing DKs. Meaning if you already have, say, a 91 DK and you want to add Wi-Fi capabilities, you can get the evaluation kit and plop it on top. Same for 5340 DK, etc. And then lastly, we have an expansion board. This is kind of like a dongle that you can put in the Thingy 53 to add Wi-Fi capabilities to the Thingy 53 prototyping platform. We also have the Nordic Power Profiler Kit 2, which comes with a Power Profiler software. So you can connect the kit to your development kit and then visually see the power consumption over time. And the Power Profiler Kit allows you to measure low sleep currents as well as the higher active currents and short current peaks on all of our Nordic DKs as well as external hardware. And as for Wi-Fi support in NRF Connect SDK, there are a lot of resources that I want to mention. First of all, we have a Getting Started with NRF 7002 DK guide, which is very useful once you've gotten the development kit. Before taking the course or watching this webinar, you should go through that guide. And we also have a rich set of Wi-Fi samples that work out of the box with all of our development hardware. I have a list, or the list of all the Wi-Fi samples are to the right here. There are also networking APIs available in Zephyr. And then we also have an NRF Wi-Fi provisioner application. So it's an app you can get for either Android or iOS, and it lets you provision the device to a Wi-Fi network using either Bluetooth, or you can use Wi-Fi or NFC. So that's a very useful tool that's nice to be aware of. Now we're going to move on to the hands-on portion of this webinar. So as I've said, the hands-on session, so the exercises or the applications that we're going to be making here are based on the Wi-Fi Fundamentals course in the Nordic Developer Academy. They're based on the exercises from lessons 2, 4, and 6. And the Wi-Fi Fundamentals course has only been out about 10 months now, and it already has over 1,000 people enrolled, and it has an average rating of 9.3. So if you find the exercises or the applications that we're going to be making useful, I definitely recommend going and checking out the full course. It's 6 lessons, and it should take about 8 to 10 hours to finish all the exercises and do the quizzes and get the full certificate. This is going to be in 3 parts. In the first part, we are going to start from scratch and then make an application that connects to a Wi-Fi access point. and also set up the configuration so that the credentials are securely stored on the device. So basically provisioning the device onto a network. In the second part, we are going to use the MQTT API in NRF Connect SDK to connect to an MQTT broker. And then after we've connected to the broker, we'll publish and subscribe to topics to be able to send commands to the device to turn on the LEDs and be notified about button presses. And then we're going to add TLS to secure the connection. And then in the final part, called Optimizing for Power Consumption, we are going to use a power profiler kit to measure the average power consumption on the device. And then we're going to enable legacy power save mode and see how that affects the power consumption. And then enable target wake time and also use the target wake time sleep status notification feature to be notified of the device status when the device is sleeping or waking up in target wake time. So those are the three portions here. As for prerequisites, I've added a few links here. You're going to need some development hardware. Either the course and the exercises support either the 7002 DK or the 7002 EK with a 5340 DK. You also will need a Wi-Fi 6 access point with target wake time support for the last portion, just to be able to enable target wake time on the device. That needs to be supported on the access point. And then for the last portion, you also need a power profiler kit. And for software, in the second portion, we're going to be using an MQTT client on the computer called MQTT Explorer. So we can connect the computer to the MQTT broker and retrieve the messages that the device is posting to the broker. You're also going to need NRF Connect for desktop for the Power Profiler app in the last portion. And you need NRF Connect SDK, of course. The course supports version 250 to 261 and Visual Studio Code with the NRF Connect SDK extension. That's all the software I will be using in this portion. Okay, so in the first portion here, we are going to connect to a Wi-Fi network or a Wi-Fi access point. And we do this in 3 steps. First, we want to create and register a callback for the network management API so that the application gets notified upon a network connected event or disconnected event. And then we want to enable shell commands, so we're able to send Wi-Fi commands to the device through the command line interface to be able to securely provision the credentials that way. And then lastly, we are going to, in the or the project conf file, we're going to configure the backend for storing the Wi-Fi credentials. So in this application, we're using the following APIs. First, the network management APIs, which is an API that allows us to call defined network routines or receive notifications on relevant network events. So we're going to use this to be notified of a disconnected or a connected event. We're also going to be using the Wi-Fi credentials library. So this is a library that allows you to store the credentials on the device, either using Zephyr's settings subsystem or platform security architecture, which is the one we're going to be using when you're building for non-secure devices. So you're building with trusted firmware management. We're going to enable this backend so that the credentials are securely stored on the device. And this library also has a shell interface or shell command, so we can send those to add the Wi-Fi credentials through CLI and then connect without having to actually store the credentials statically on the device. So let's find the application I'm going to be using here. We can start with the first step, which was create and register a callback for network management. That is as simple as here we are defining the callback structure, and here is our event handler. And we have created, or we are interested in the following 2 events, net event L for connected in which case we want to log network connected, and we want the DK on the device to light up as well. And we also have a disconnected event to let us know if the device gets disconnected from the network and turn off the LED. And then in main, we just register, initialize, and add these this callback in the event handler. And then I have a semaphore defined that we take here, so the application waits, and then it's given when we are connected. So the application waits until the network is connected to go further. And then in the project conf file, the interesting ones are these, where we're enabling the network management API, and these two for actually being able to get notified of these events, and then setting the stack size. Here we are enabling Wi-Fi and the WPA supplicant, which is necessary to run the Wi-Fi stack. And this is for the Wi-Fi credentials library. And then here we're enabling the shell interface. So first the general shell interface, and then this is to enable the commands to send Wi-Fi scan, Wi-Fi connect, stuff like that. And then this one is to send the shell commands specific to the Wi-Fi credentials library that we're going to be using. And then lastly, in the boards folder, we have specific overlay configurations. So there's one if you're building for the non-secure target, so with trusted firmware management, and one without. So the one with, we're setting the backend of the Wi-Fi credentials library to use PSA, and then setting the partition size of the trusted firmware management memory, and increasing the heap size of embed TLS. And then if you're building for the secure board, you want to use the settings backend, and then configuring the flash and non-volatile security and things like that. So depending on what you're building for, one of these will be invoked. So then we can actually just add folder as application, add the build configuration. I'm going to be building for the non-secure board because that is building with trusted firmware management, which is more secure, so it's recommended. And then build. Okay, now we go to NRF Connect for desktop, and we want to open a serial terminal. You can also open a terminal in VS Code. I just prefer this one. Connect to the DK, press reset, and then we can see if the shell interface has been enabled by sending a command to scan for available access points. Yeah, so that's good. And then let's show the commands here while we're working. So here are the supported CLI commands. First, for the Wi-Fi command line commands, we have scan. We can call connect and disconnect. But the one we also enabled is Wi-Fi credentials, which is an extension. So now we can call Wi-Fi cred add, and then we can add the credentials of the SSID. We want. So that's added to the list. If we call list here, it comes up. And then we can call auto connect, and it should automatically connect to the network even upon reboot. And that's it. That's the first part. So for this next part, we are going to configure the device to subscribe to an MQTT broker or connect to an MQTT broker, and then we are going to use or set up an MQTT client on our computer as well, so we can publish and subscribe to the same topics, to be able to change the LEDs and monitor the button status on the device. And this is all going to happen over TLS, so a secure connection. So for this, we are going to use, first and foremost, the MQTT client library in NRF Connect SDK. And this library lets us set up the device as an MQTT client. So we will configure the device as a client, and then we're going to connect to the broker, create the MQTT handler for different events, publish to topics, subscribe to topics, and then keep the connection alive using a specific API call. And you can also, this library also supports adding TLS. And to do this, we're going to use the secure sockets subsystem. In the sockets API we're already using, TLS credential subsystem, to pass the service certificate to verify the connection when we're connecting to the broker. So we can take a look at the different configurations. We're enabling the library, enabling TLS. Here we're defining the topics that the device will publish and subscribe to, and the port. And then we're enabling the TLS credentials library. Here we have the certificate that we're using to verify the connection. The certificate is taken from the website itself, and then we used a script, a Python script that's found here to convert it to a header file. All these steps are detailed in the exercise itself. And then for the main, the interesting one is the event handler for the MQTT library, where upon a publish event, we publish to the broker. And again, the steps in the lesson 4 of the course will go through this in a lot of detail to understand every single aspect. We are limited to 45 minutes today, so I just want to show you the gist of it. So here we can see that if we're pushing button 1 or 2, the device will publish to the published topic with the configured message to say button 1 has been pressed or button 2 has been pressed. Here's the API call for adding the credentials for the TLS connection. And then in the while loop in the main function, we are polling for any messages, and then we are calling MQTT live to keep the MQTT connection alive. So let's add this as an application and build and see how it works. Okay, let's open the serial terminal again. Okay, let's reset the device. And then we want to connect. As we can see, the credentials are stored here in the Wi-Fi credentials library. So we just call connect to request the connection. Okay. So now it's subscribed to the topic for controlling the LEDs. And if I press a button now, it should publish to the topic to let us know that the button has been pressed. So what we're going to do now is open up MQTT Explorer. Here we have the MQTT Explorer. So we want to set up our computer as an MQTT client connected to the same broker. And here we're also enabling TLS connection for security. And here I've added the topic that the button is publishing to as our subscribe topic, so that we'll get notified when the device publishes to this topic. So let's connect. And then we can also add in Let's send a message to the topic that the device is subscribed to. And we can send LED1 on, for example. And publish. And we'll see that the device receives that. Let's do the same for off to turn it off. And it's received. And then if we press the button on the device, we'll see here that the device published button 1 pressed to this topic. So now we've come to the last part of this hands-on session, optimizing for power consumption, where we're going to take a power profiler kit and connect it to the device to measure the power consumption while we enable different power saving modes, and see how we do this with API calls. We're also going to use target wake time sleep status notifications to notify the application when the device is sleeping and when it is awake. And for this, you need a power profiler kit. You also need a Wi-Fi 6 access point with target wake time enabled, at least for the last part to enable target wake time. And then you need the power profiler application in NRF Connect for desktop. So before we start with the application, I thought I would just show you what the different power saving modes, what they are, first of all, in a bit more detail, and what they look like with regard to power consumption. So I've just flashed our solution from part 1, which was the application where you can send shell commands to the device. And then I have a terminal here running so we can talk to the device. And then I'm going to connect the power profiler kit to the DK. So for that, we want VOUT, the VOUT pin from the power profiler kit, connected to pin 23 on the device, or P23. It's the one next to the debug out port. And then we want ground connected to P21, and make sure the device is plugged into the computer with the USB data power port, not the one that says power only. And then we're going to open the power profiler application. So that's in NRF Connect. NRF Connect for desktop. It's this application. Select the power profiler kit. We want source meter, and then set the supply voltage to 3.6 volts, so 3,600 millivolts. Enable power output. And then for sampling parameters, I just chose 10,000. And then let's start. So here we have the power consumption, and then we can send commands to the device simultaneously. Okay, so here we have it going. And then we can send commands to the device. So first we're going to start with sending Wi-Fi scan. So we can see what a Wi-Fi scan looks like. So we can see here that this is the scan on the 2.4 gigahertz band, and then this is the scan on the 5 gigahertz band. And for the 2.4 gigahertz band, we can also see it's sending out probe requests into the different channels, and then seeing the response. And then I'm going to connect to the SSID, the network I have that supports target wake time. Now it is connecting. And here we can see that it is in DTIM mode. So it's waking up for every DTIM beacon that the access point is sending out. Which is about, let's see. Yeah, 3 seconds. So what we can do, there is a command called PS, power save, where we can see, so power save status, power save is enabled. We are in legacy power save, listen interval, and then the wake up mode is DTIM. So there is actually another way to lower the power consumption in using legacy power save without having to use target wake time. And that is something called extended power save mode, or wake up mode listen interval. So basically, when the client initiates the connection with the access point, they discuss, or they exchange this listen interval, which is how often the device can skip a DTIM beacon. So it can sleep for a longer period of time and then wake up for some of the DTIM beacons. So if we now call PS wake up mode listen interval, we can see that if you see here in the panel to the left, it's skipped. It's skipping now only waking up for every third DTIM beacon, it looks like. So it's saving much more power than previously. We can also change the listen interval, but to do that, we do need to disconnect from the network, because this is established when the device connects. So if we disconnect, we can call let's see, if we do 30 maybe, and then if I click up here, I should find my connect command again. We connect, and when the device has connected, we can see that's waking up much less than before. And if we now change the wake up mode again to DTIM, we can see it starts waking up more often again. Okay, so now let's take a look at the application code that actually does this. So I've split it into two parts. We have the legacy PSM, and then we have one for enabling target wake time. So first, let's look through the application for enabling power saving modes. This is based on the one we made for part 1. So we have our network management event handler, but we've defined 2 booleans to keep track of power saving, to keep track of if the power saving mode is enabled and what the wake up mode is. And then we have a function for setting the power state. The first thing we do is we get the network interface, because whenever you're sending a network request in the network management API, you have to attach a network interface to it, since the network management API handles many layers of the network stack. So here we're defining the interface, and then we define the parameters, the Wi-Fi PS params structure, and we are setting its member enabled, either to enabled or disabled, based on what the state was previously, because we want this power state function to toggle the power state. And then we use the API call to net management. This is the same one for any request you want to make, and then the first parameter, you define what kind of request it is. So here we're saying it's a network request Wi-Fi power save, and then we pass the interface and the parameter, and that's pretty much it for setting the power state. And then for setting the wake up mode, it's very similar. We get the network interface, and then we define the parameter structure. And then here we're looking at the wake up mode. So we take the wake up mode member of the structure, and we set it to either DTIM or listen interval based on what it was previously. And then we also have to set the type to wake up mode. And here again, we send the same network request to network management, Wi-Fi power save with the interface and the parameter. And that's it. And then we've set in the button handler, button 1 sets the power state, and button 2 changes the wake up mode. So let's build this and see how it works. So now the application has been built and flashed to the device, and we have a serial terminal up to see the log output. Okay, now let's see if our credentials are still, there they are, so we auto connect. Okay, connected, and then we want to connect your device again, and click start. Okay, and then we can now press button 1 and set the power save mode, or disable the power save mode in this case. And then we press button 2 to enable it again. So now we're in DTIM mode. And then we want to press button 2 to go to wake up mode listen interval. And then again to go back to DTIM mode. Okay, now let's open the one with target wake time features, and let's go through that one. So when enabling target wake time, we actually want to register another callback with the network management API. So here is a mask of all the events we are interested in. We are interested in the target wake time event, which is when a target wake time flow is initiated or teared down. And then we are also interested in this sleep state notification. And this is a functionality where the application can be notified when the device is going into sleep and is waking up in relation to target wake time. And then we're setting the wake interval and the interval here. So the wake interval is how long or for how long the device wakes up, and then the interval is for how long it's sleeping. And then we want to define our callback structure, and let's see, this is just printing a lot of the information from a TVT event. Here we have our event handler. So this is for logging all the info when there is a target wake time event. And then here, once we get a sleep state notification, we'll log that as well, so we know if we're awake or sleeping. And then set TVT, here's where we actually set up the flow. So very similar to the other two functions, wake up mode and power state, we get the network interface, we set up the parameters. In this case, it's the Wi-Fi TVT param structure, and there are a lot more things to configure. So we want to set a request command, and we are setting up a target wake time flow here. And then since we want to reduce the power consumption as much as possible, we want to reduce the amount of messages sent, so we're disabling trigger frames and configuring target wake time to be implicit and unannounced. So the device doesn't have to send a trigger frame to the access point to inform that it's awake and ready to receive packets. And we're setting the wake interval and interval in microseconds. And then here we are tearing down the flow. And as usual, we're sending this as a API call to the network management API with the request type Wi-Fi TVT. And we are registering the target wake time callback in the main function. And that's pretty much it. Let's change. So we set target wake time. We'll press button 2. And then we can build and see how this works. Let's see. Add it as an application. And pristine build. So we have the Power Profiler running and the application. Let's just connect to the network and wait for that to get connected. Now let's see if we can set up a TVT flow. Okay, there we go. Let's see. Accepted. And we got the wake interval of 65 milliseconds and the interval of 7 seconds. And we have our sleep notifications. So let's see. If we see the sleep time here, yeah, 6.8 seconds. And you can see it's drawing very little current and then it's waking up for a very small amount of time. And going back. Okay, now we're at the end of the session. So to recap quickly, the applications that we have gone through today are all taken from coding exercises in the Wi-Fi Fundamentals course on the Dev Academy. So if you're interested to learn more, definitely go check out that course. Now for the Q&A session, please welcome my colleague Finn.
Hi.
It doesn't look like we have any questions yet. Feel free to input them. While we wait, I can talk a bit more about what the Wi-Fi course covers. So the Wi-Fi course also covers, there's a lesson about HTTP where we learn both how to set up the device as an HTTP client to connect to an HTTP server that is hosted by the Dev Academy, but then there is also a lesson about how to set up the device as an HTTP server, which is very interesting. Okay, looks like we got our first question. What kind of battery do you recommend? Do you want to take that one, Finn?
The main thing is have a look at what you want to use. Be aware that 5 gigahertz takes more current than 2.4 gigahertz. So don't just look at your average power consumption, look at your current peaks and make sure your battery chemistry supports that. We talk a bit more about battery chemistry when we talk about PMIX. So both Heidi and I aren't the absolute experts, but it's always safe to just go with a LiPo battery, for example. And if you, it then depends on how long of a battery life you want to. If you just do like 300 or 600 milliamp hour battery, that is good enough for basically anything you want to do in most cases. Well, that's a rule of thumb.
Okay, and then the next question. Yeah, in the examples, they were individual, but what's the impact of using target wake time with MQTT in long periods? So MQTT has support for a keep alive function, which means that there's a period of time where the client does not have to connect to or communicate with the broker, but the connection is still kept alive. And that keep alive time, I just looked it up, it's actually 18 hours. So that is the maximum amount that you could then sleep in target wake time and still have the MQTT session be alive when the device wakes up again to communicate.
Okay, if we don't get more, it might be worth mentioning that once we upload the on-demand versions of this, we actually at points in time have a look at the comments that we get under these videos and answer questions like that. Oh, but we do have another question here. Yeah, should I take that or do you want to, Heidi?
Go for it.
Yeah, so this is actually, so like in most use cases, when you use Nordic for Wi-Fi, you're not gonna want to use the maximum throughput anyway. So a lot of the things that we do for Wi-Fi, like OFDMA, for example, are targeted at actually using slower speeds. And then you wouldn't run into the problem that you need to have the QSPI connection and can just use SPI and could use QSPI for external flash. But I think you can also have external flash via SPI, but even though like it's not recommended. But yes, it is a problem and something to be aware of. just to say.
Okay, and the next one, does the device support 40 megahertz bandwidth? So the answer to that is no. The NRF 7002 series supports 20 megahertz channel bandwidth.
Yeah, and the answer is also more along the line of what I said before. Like usually we would rather use less of that than more. So like a lot of the use cases, especially like things like OFDMA, for example, we're actually trying to use less than 20 megahertz just so we can like send more information like with different devices at the same time. So there was no reason for us to go higher when we're actually trying to go lower most of the time for power saving.
Nice, thanks. When developing a customized PCB with a Nordic host controller, how easy can a software example be ported from the dev kit examples? That's a very good question. So in the Dev Academy, we have a lesson in the NRF Connect SDK intermediate course called how to make or developing with custom boards, which teaches you how to make a board target for your custom board. And then usually porting a software example is as easy as building that example for the custom board target. So they're very easily portable. You just have to build for the board you want the application to run on. So the challenging part is making the board folder, but we have, as I said, a lesson for that to make it easier. So,
and I think we also have a dedicated webinar, right?
Yes, we have a dedicated webinar for that as well.
Yeah. And then one last question. Here I'm actually not sure. Do you know the answer, Heidi?
I do not know.
Okay. So one thing to mention is it's not the intended use case for soft AP. I know and have talked to one of our customer who did this with more than one device, but the honest answer is I don't know. We would have to look it up.
So I did look it up, and it's 8 station connections. That's what's supported. But as Finn said, that's not the recommended. The recommended use case for soft AP is to provision for Wi-Fi provisioning, to provision the device onto the network.
I don't think that's a secret. So this one is on the same process size as our 52 series, I think, which should be 55 nanometer. Don't quote me on that. That is, I'm pretty sure that's the correct one. I'm not 100% sure though. But it is not on the 20 nanometers or 22 nanometers, 20 that we have for the 54 series. So it's still on the old process node size.
Okay, Thank you. And for the next one, what is the maximum target wait time which is supported? So our SDK currently supports an interval of 35 minutes right now. And if the client remains synchronized to the access point, depends on how long it sleeps. But if it does sleep for a period of time, then it does have to wake up and resynchronize with the access point before continuing.
Yeah, and it resynchronizes itself infrequently while listening, through listening to the beacons. That also answers the next question, I think.
Yes. How does the access point ensure that it doesn't get out of sync with the NRF after target wake time was negotiated? Yeah, that's by listening to the beacons that's sent out by the access point.
Yeah. And the next question, let me just maybe just if you put my camera on, I can actually show it quickly. And you just click on my picture, and everybody should see that. Because I have a kit here, obviously. So this is the DK that you've asked about. So the question was, if I understood correctly, the NF 7002 DK don't have Wi-Fi antennas by itself, but it actually does. So we have looks the same as the 5340 DK, but we have two antennas. So this is the antenna we use for Bluetooth and everything, and this is the single band or the dual band Wi-Fi antenna that we're using for 2.4 and 5 gigahertz. So it does have the antenna in itself. So you don't need to add any extra antenna. This kit in itself will be enough. So no extra antenna needed. Hope that answers that question. Good.
Okay. If there aren't any more questions, we can wait a few seconds. Anybody has anything? Nope. Then thank you so much for joining, everyone. And thank you, Finn, for joining.
No worries. Thank you. Bye.
Bye, everyone.